Alright, so for today will be Chapter 7 and Chapter 15. Chapter 7 will be part of the next chapter. So search on page 121. So first off, what is pitch?
I got that highlighted in this one.
You got it highlighted in there, right?
Can I give you a definition from the book?
There's a definition in the book, right? There is a definition as to what is pitch,
The
right?
attribute of auditory sensation in terms of which sound may be ordered on a scale extending from low to high.
Right. Very good. You read well. Okay, right?
I feel like such a fool sometimes.
Right. Can range the sound from low to high, right? So this chapter deals with the first part in terms of pitch. So you have on page 123, they have in terms of a lovely graph, another one of their graphs that they like to use in this book. And it actually is part of one of the questions you have for your homework. This one, let's see, we got one curve that goes like this, which is this curve is J and D. Just noticeable difference. And then the other curve they give you looks something like that. And this curve they tell you is the critical band. Right? Right. So the scale they give you is that this is the change in frequency here in hertz. The bottom scale is the frequency. Okay. So you get in terms of frequency resolution, which is given by this. Resolution is given by delta F over F. Right? So you do have one of your homework questions that deal with this graph. And again, part of it is, again, trying to read numbers off of this graph because of the way the scale is. So it's going to be hard to be perfect. Okay? But for example, you have, let's say, for example, from that graph, say at 200 hertz. Okay. So at 200 hertz on that graph, you go up on the J and D side first. So you start at 200. So for example, let's say that this was 200. We go up. You then would read across and get that number. And roughly that corresponds to what? Okay. And And again, given the scale, yeah, you're sort of going to have to give or take a bit, right? Because the scale's not that great. So you're better than 2, but not quite 3, right? So you pick a number somewhere in that range. So you'd say, oh, let's go like, what, 2.3 or so? Pick a number, really. Okay? All right. Now, if you go all the way up to the critical band number, what does that correspond to? So now you just follow it up, right? And you're less than 100, right? 99. Okay, that's less than 100. 98.9. Ooh, that's pretty good given the scale on this graph that you can actually get it to 98.9. Right? But again, the next part is just take this line, go up, and again, read across. Okay? And again, given the scale on that thing, you're sort of, yeah. Again, given the scale, yeah, there's, there's leeway on it, give or take a bit. And then once you got those numbers, we can look in terms. So like here, if we said this was what, 98.9, I don't think we're going to quite go that accurate. Given that scale, let's go with this is like 98, right? So if I want the resolution, in terms of this, it would be 98 divided by 2 point. Right. That's right. Right. So delta F is going to be in terms. So what is the ratio of our 98 to 2.3? How much?
42.6.
42.6, okay? So if I do 98 over 2.3, yeah, what, 42.6?
Yeah.
So roughly 42.6, right? Now in the book, they tell you on 123, second paragraph, third paragraph, right? Comparing the upper and lower curves, the critical bandwidth is roughly equal to 30 times greater. So this one we got 42.6 based on our numbers and our reading of that graph. Well, the ratio of the numbers should come out to be on the order of 30, they tell you. Or so. But again, you do have a question dealing with that graph. And again, it's subjective as to how you read it. And, okay. Okay. Everybody knows Pythagoras, right? Everybody's heard of Pythagoras at one point in time. Okay. Okay. I know everybody's probably heard of the good old Pythagorean theorem, right? A squared plus B squared equals C squared. He also said that in terms of this, if I have a string of a given length, right? Maybe now it's a complete string. Okay. So let's say in terms of the string that it is 90 centimeters long. And then if I divide it up, so then we now make it so that there is another fixed point there. And if the ratio is 2 to 1, that the one will be 1 octave greater than the other. So if this string is 90 centimeters in length, where do I divide it up? Be 60, 30, right? This side will be 60 centimeters. This side will be 30 centimeters, right? And in terms of sound, the difference will be in terms of 1 octave. Everybody knows where the 60 and 30 comes from, right? After all, there will be a question like this on next week's test. Right? Given a string length, tell me where would you divide it? Yes?
Can you remind me where the 60 and 30 comes from? I know it comes from the 90, but...
It comes to the 90, okay? So mathematically, how do we get the answer? Other than people can probably look at it, so people who did this and gave me the number probably could tell me right away what the numbers were. But mathematically, how do you get the numbers?
Well, you have a 2 to 1 ratio, so one is twice as big as the other. All you gotta do is add the 2 of the ones, and then divide 90 by 3. And then, so you have 30 there, a 2 to 1 ratio, 30 more 30 is 60, 60 to 30.
Right. So if I'm going, yeah, so again, if we're talking a ratio of 2 to 1, we're actually talking out of 3 parts, right? So the common mistake is to, again, is not to think about it that it's out of 3 parts, but out of 2 parts. And of course, that doesn't work because you don't end up with the right answer that way, okay? So it would end up being 90 times 1/3, or 90 divided by 3, which will give you the first part. And of course, once you know the one, you know the other because they have to add up to 90. So if I do that, I get 30. 90 minus 30 gives me the other part, which will be 60.
And cutting it there just makes it 1 octave higher.
Right.
Cool.
Yep. Yep. So the So in terms of waves and waveforms, okay, you get in terms of complex waves. So we have, everybody's used to seeing the good old sine wave, right? That thing. But there's other waveforms out there. You can have in terms of square waves. Okay. Very dotted writing. So square waves. One more. have in terms of
What's something I always call it triangle waves? I don't know why. What's the name of it? Other than like the super complex, like real waves.
well, maybe not. Doesn't show up. Yeah. Okay. So you get in terms of wave types, triangular waves, sawtooth, square waves, half sine, and
What's
so
that
on.
fourth one?
This one,
Absolute.
absolute value. Right. Okay.
Oh.
Okay. Now, in terms of these complex waves, you got in terms of Fourier. Well, basically said that any complex wave can be written as the sum of sine waves. Just add it together.
The harmonics.
Yeah, if you add all the harmonics up, you'll end up at a given. Yeah. Okay. Okay. So if you think specifically in terms of like the first three, not really the bottom two on there, but you got triangular waves, sawtooth waves, square waves can be written as the sum of sine waves. Okay? Now, without worrying about the lovely mathematical equations that are on there, okay, we won't make you do that math. Okay, but because basically Fourier analysis is done in terms of calculus and solving for the various constants that go with it. Okay? But basically, you got that a square wave is just a number of sine waves added together.
That's calculus, everything.
To do that, yes, it would be calculus. Fine, well, we okay. But actually, it would be a few calculuses down the road. From okay, so now we're not going to do it in next quarter calculus class. Okay, that's a little bit down the road for that one. Do that stuff. Okay. But you can look in terms of waves and break them apart into various sine curves that come up with that wave. Right? So you can get in terms, fast Fourier transforms. That can be done on a sound source. And you can break it down as to what harmonics are present in that sound. And that'll vary in terms of instrument type, so whether or not it has all harmonics or just odd harmonics. You would see that in terms of that FFT. Open show. Okay. Right. So in terms of this stuff, we're going to watch a segment of a video from MIT. Again, don't get bogged down in the math part that he's doing. After all, it is from MIT. Okay, so don't worry about math, but he does have a good demo thing that he does dealing with this and how it works for this process of putting together sine waves to come up with these complex waveforms. Hold this up. All right, let's see here. So this comes off of the MIT website. MIT has what they call their open courseware. So practically all their courses are posted there. So you can look at their stuff. They also, depending on the course, some of them have video lectures with them, some don't. So there are those. Also, if you're looking for other places to pick up other additional information, there are those edX courses. Everybody knows what those are? edX. It's a bunch of colleges, basically all over the world. And they post information, post courses that you can do covering a variety of topics, from social to math and science related. And they're free and open courses. Posted from people from like Harvard and MIT and Berkeley and all those sorts of places. But it's another good way if you want to pick up some additional information, various topics. Right. Alright, so again, this part we'll deal with the Fourier analysis part that does do a couple good demos on how it works in terms of a computer program that he uses, really showing how a triangular wave propagates on a string, and then how that wave can be reproduced by using a sum of sine waves. But again, here you've got it up here. Don't worry about this math part, okay? Anybody in here taking calculus next quarter? Just Casey? No, nobody else? You'll see that symbol next quarter in calculus, that curve, which is for integration. Okay? Nobody else signed up for calc? Come on. Come on, after all, you only do two things in calculus. You find slope and you find area. Anyway, that's all you do. It's slope and area. Okay? Of course, the way you find slope and area is a bit different, but that's all you're doing is you find slope and area. Okay? And basically, calculus itself is a trick. Really. Right? It's magic. Because in calculus, you learn that you can divide by 0 and actually get a number.
You can't divide by 0.
You can in calculus.
I hate school, man.
Calculus is the rest in the universe.
Okay? And then also in calculus, you find out that you can multiply by 0 and actually get a number.
Are you kidding me, man? Why do they even teach us this shit if it could be teach? I don't understand. That's like telling kids Columbus found America. That shit ain't real, man. God damn.
Alright? So that's basically what calculus does. It's a trick. Okay? And basically one of the reasons why we have calculus goes back to good old Sir Isaac Newton. How we got ended up with calculus. Alright. So let's get this rolling here.
Yeah, obviously, Isaac Newton loves fucking with everybody. Excuse my language. I gotta learn to turn that phone on.
getting no sense.
And I'll be with it.
Yeah.
As 4a divided by m pi.
Okay.
I could write it down as simply as pi. And then I get here the sign, pi x divided by L, plus 1/3, that is that m equals 3, which is 3 times lower, because you have an m3 here, times the sign of 3 pi x divided by L, plus 1/5, and then you get the sign of 5 pi x divided by L, and so on and so on.
Makes so much sense now.
Okay.
So now I would like to put in my function, I would like to put in the first 2 terms. And I will do that here on the blackboard. So I'm going to concentrate now only on my function 0 to L. In reality, it's only here.
Alright.
And now I would like to put in there, and this is A. And now I would like to know what is B1. Well, B1 is going to be 4a divided by pi, which is approximately 1.27a. Well, let's put it in there. This is A, so I have to put in 1/3 more, so it comes up to this point roughly. So there it is. I love it. It's not quite a square yet, but we're getting there. We're on our way to building up the square. The next one is B3. B3 is 4a divided by 3 pi. So it is 1/3 of 1.27, which is about 0.42 a. And B5 is 1/5 times B1. Let's put in B3. So B3 has an amplitude which is about 0.4, which is about this much. It's about the height, 0.4, a little lower. And so here we have the maximum, and then we have a 0 here, we have a 0 here, and so we have here, and then we go to this point. So the curve is something like this. So this now is B3, and this is B1. Now look at B3. Look at the beauty of Fourier analysis. This is higher than it should be. Oh, B3 says, I'll take care of that. I will subtract something there. We'll take that off there. Isn't that beautiful? So you're going to flatten this out already. Already with 2 terms, B1 and B3, you're already beginning to see the building up of this crazy square. And look here. B1 says, sorry, I cannot fill this up for you. This is the best I can do. B3 says, I'm going to help you. I'm going to help stuff there. And it's going to do the same there. And so you see that if you now keep adding odd values of m, that you will gradually approach that square, which is an amazing concept. And what I will demonstrate to you is making a square, and we will make it like this, just like we did here. We can do that on an oscilloscope. We can have a signal that makes this trace. Admittedly, this is time, but the way you will see it is space, so you can think of it as being space. It's no different from the function that we had. And then we will show you the B1 value. In this case, since it is in time, it actually has a frequency. It's 440 hertz. We can make you listen to it. And then we will show you the B3 value, which has 3 times higher frequency. And then we will show you the B5 and the B7 and the B9, And then we will add them all up, and you will see it begin to look like a square. And so, let us set that up. Supposed to see that on the central there. What you see here is simply the B1. So you don't see very much, do you? You just see a sine curve. Well, you're looking at this sine curve. Now I'm going to show, actually, can we hear it, the Markos? Here's the 440 Hertz. Now I'm going to show you the B3. Notice it is 3 times smaller in amplitude. That's the way we set it. As a 3 times higher frequency. And now I'm going to show you B5, which is 5 times smaller than the, hold it, no. Okay, it's 5 times smaller than B1. And the frequency, of course, is 5 times higher. You can hear it. Yeah, this, there it is. And now I'm going to show you 7. 7 times smaller than B1. And here is B9, 9 times smaller than B1.
Barely.
And now I'm going to show them all 5s to you. And it's really beginning to look like the square pose. It is clear that B1 is very, very important. So if I take B1 out, which I will do now, it doesn't even look like a square. That shows you how important that first term is. If I take B3 out, that is less disastrous, but it is still pretty disastrous. But you already begin to see something that looks like a square slope. And it should be clear to you now that in order to get the real sharp edges here, you need very high harmonics. You have to go to M values of 49, 101, 201. They're all odds. You have to go to very high values, and the higher you go, the closer you will get to the square. So this is a nice moment to have a break. And I know you're dying to do your 5th mini quiz. I will hand it out now, and then we will all start at the same time with the mini quiz, so that each one of you has the same amount of time. I owed you the histogram of the exam. You see that here. I think it's a wonderful histogram as far as I'm concerned. It is too early to talk passing and failing and A, B, C's and D's, but if I knew nothing else, no other grades, then I would have to put you in the danger zone if you score less than 45. That's all I can say. I can add nothing more than what I already wrote you by email. So let us now return to our string. Our string is still at t equals 0. So our string is still in this position, dying to be released. That was the goal. Remember, we would pluck it and we would let it go. At time t equals 0, this is the Fourier analysis. These are the Fourier components of that string. But now I say, okay, go. And what happens now is that this one is going to oscillate with omega 1t, and this one is going to oscillate omega 2t, and this one, omega 3t, and this one is going to oscillate with cosine omega 5t. Each one of these are standing waves. And so each one of these are going to do this with their own amplitude and with their own frequency. And omega m is going to be v times k of m, and the speed of propagation is the square root of t divided by mu. And that's what's going to happen. So now, you may wonder what you're going to see if you let this spring go. And chances are, if I ask you what do you think will happen, that you may think that this will happen with the string as a whole, but that's not true. And the best way actually to answer the question what you're going to see is to go back to a simple case of a triangular pulse on a string. If I have a triangular, I'll do that here. If I have a triangular pulse on a string, I exaggerate, of course, the amplitude highly, fixed here, 0, and fixed here at L, and I let it go. Yes, I can decompose that in terms of the Fourier components, and each of these Fourier components are going like standing waves up and down. It doesn't give me much insight, but it is intriguing that that's what happens. I can also think of it that nature is seeing a disturbance, and it says, well, we're going to propagate this disturbance. Nature doesn't know the difference between left and right. And so clearly what will happen, if this has an amplitude A, there will be a pulse with an amplitude 1/2, which goes in this direction, and one with the same 1/2, which goes into that direction. And that is exactly what you're going to see when you let it go. So a little later in time, you will see this going in this direction, going in this direction. At the moment that the top of this mountain reaches L and the top of this mountain reaches 0, you're going to see nothing, absolutely nothing, because the reflected one and the incident one exactly cancel each other. And then a little later in time, they will be on their way back. And then a little later in time, you will see this one, but completely flipped over when these two triangles meet each other. And so that's when you will see the thing upside down. So there are two very different ways of looking at what happens when you release a plucked string. One way is to say there are oscillations of standing waves, a la Fourier, and the other way is to say, well, we're going to always cut it in two pulses, each of half the amplitude, and let them go back and forth and let them reflect at the ends. Now keep in mind that standing waves are the result of the superposition of traveling waves. So the two different ways of looking are of course connected. They have the same underlying physics. And now I want to demonstrate this to you using a program that was developed by Professor Rietslaus when he was lecturing Edo through, and also Nurgis. I think she's in the audience. Nurgis, are you hiding? Yeah, you're hiding. Nurgis has also worked on this program. It's a wonderful program. I'm going to put a triangle first on a string. The width of the triangle is about 1/3 of the length. And then I will release it and I will let it go. And we will see the Fourier components. And at the end, when the whole show is over, after 1/2 the time for the fundamental period, we will wait 1/2 period of the fundamental, we will inspect very closely the Fourier components. Because of the symmetry of this problem, all even values of m will have 0 values of v, and you will be able to see that. Now, were we going to change the light setting for this, or were we not? No? I thought we would. Why don't you turn that off also? Oh, that's too difficult, perhaps. Yeah? Throw the bar. No, the bar.
Ah! That's crazy.
All right, so what you're going to see first is the triangle. The number of Fourier components that we have is 25. Do I do something wrong? Excuse me? Oh, we know what? You broke the line? Oh, that's nice. Thank you. The number of terms we have is 25. We have m equals 1, m equals 3, m equals 5, all the way up to 49. That's when we cut it off. All even values for m have no b value. And if you're ready, I'm ready. So let's first run this one. There you see the triangle, and the blue lines are the Fourier components. They are each doing this thing, their own thing, standing waves up and down. But the net result is something that you're quite familiar with. You see two pulses with half the amplitude of the original one. They move to each their own side, they reflect, and they come back. And then we will stop when we have half the period of the fundamental. Now look at the individual Fourier component. This is B1. And this one is B3. You see, it helps building up that triangle. This is B5. It helps building up the triangle. This is B7. And this is B9. And here they all conspire. Amazing. There are 25 sinusoids that are conspiring there, and they show you nothing. And the same here. And it's hard to believe that all these sinusoids can add up to 0 here, and how beautifully they connect here. And the only reason why this tip is not very sharp is we only have 25 terms. If I would run it with 400 terms, then you would see this sharper, but it would take a lot more time. Let's look at the Fourier components, which you will see here. So this is B1, which we have arbitrarily called 1. You see all the even values. This is B2, B3, B2, B4, B6, B8. All the even values are 0. The B3 is negative, in this case. That was not the case for our square. Remember, in the case of the square, B1, B3, B5, B7 were all positive. They all had the same sign. That's not the case with the triangle. They alternate. The next one that I want to run for you is a square which has a width half the length of the string, and it is centered at the middle of the string. And again, two pulses are each going their own direction with half the amplitude. They're being reflected, and strange things happen at the ends. And now there comes a time, 1/4 of a period of the fundamental, that you see nothing. And now they're coming back from the reflection. Very different from what you expect, isn't it? Now look at B1. That's a real biggie. Look at B1. Boy, here. Is that a surprise? No, because clearly, B1 is not quite a square, but it's almost a square, right? You just have to subtract something here. Well, B3 says that's okay. I will subtract there, and B3 will subtract here. And B1 is a little shallow here. It's a little bit too, not generous enough. And then B3 says, okay, I'll help you building it up. And so if we look at the Fourier components, we see now that again all the even values are 0. B1, by definition 1, and now you see this one is negative. And B5 is also negative, not so obvious. And B7 is positive, and B9 is positive. Now I'll show you one whereby I'm going to offset the square. The square is only 1/4 the length, and I'm going to offset it. And when I offset it from the center, you need both odd and even values, and you're going to see that. So now you cannot just get away with only even values of mirroring. Here you see the wave splitting up in two, just like you expected. It has a width 1/4 of the length of the string. This one has already reflected. This one is now on its way to being reflected. Now this one is coming back. There it is. This one is already on its return. And of course they're going to meet again. And now we are 1/2 period of the fundamental later. And now look. This now is the first harmonic. Now there is also a second harmonic. M equals 2 has a B value, and here it is. This is the B2 value. Large amplitude, you notice that? And look how important B4 is. I think this is the B4 value. Yes, indeed. Here is the B3. This is the B4. Has a huge amplitude. And look how important it is, because right here where the pulse is, you need this bulge to push this further out, because the B1 alone cannot reach that point. Let's take a look at the Fourier spectrum here. Here you see B1, which we by definition call 1. You see B2 is there. It's large. It's a little larger than 0.7. And then you have a B3 which is negative, and a B4 which is negative, and a B5 which is negative. Here B4 is off scale. And now you get B6 positive, B7 positive. B8 is 0 and B16 is 0. Well, that's probably the result of the way we set up the square, which has a width of 1/4 of a length, and we offset it from the middle by 1/4 of a length. Remarkable example of Fourier analysis now, which is way more complicated than if you nicely center it. All values of B now, all values of M are important. You will now understand when I said if we pluck the string of a harp or the string of a violin and you pluck it this way, fixed here and fixed here, the tone that you hear is different than when you pluck it this way. You now understand that. Because the Fourier components of this one and this one are very different than the Fourier components from this one. And so when you let the string go, the frequencies that will be produced are the frequencies of these normal modes, of these B values. But the various B values are very different here from there. And so the sound that you hear is distinctly different when you pluck a string from the side than when you pluck it in the middle. You may remember that during that lecture I told you that the hammer of a piano hits the string about 1/7 of the length of the string from one side. That is done to suppress the 7th harmonic. For some reason that beats me, people don't like the 7th harmonic, so that's the way they kill it. So it does depend on where you pluck and where you hit. And now you can put that in context, because now you understand that you analyze the thing here in terms of Fourier components, and each one will then oscillate at their own frequency with their own amplitude. So what we have discussed now at length is a Fourier analysis in space, in x, in meters. And we decomposed a function in the sum of many harmonics, which together make up then the shape of the string. Now if we look at sound, sound of course is something that is a function in time. Suppose I look at the sound signal made by a tuning fork of 440 hertz, and I have here that signal in time. Suppose I have 1 second of data, 440 hertz, so this is now time, but if you want to think of this as being in space, be my guest. Now, there are special programs, special algorithms, that takes this 1 second of data, perform a Fourier analysis. They have a name, we call them fast Fourier transforms, and it's going to tell me what the amplitude of B1 is, and A1 of B2, and A2 of B3 and A3, and so on. If I now think in terms of hertz rather than in terms of omega, there is nothing at 1 hertz, So those A's and B's are 0. There's nothing at 2 hertz. So those A's and B's are 0. But by the time I reach 440 hertz, the system says, yappy, there's a lot of power there at 440 hertz. And what we now do, we make a plot of the square of A plus the square of B. And the reason why we square them is that energy is always proportional to the amplitude squared. And so you take the A squares and the B squares and you add them. We call this a power density spectrum, a Fourier spectrum. And here you have your omega, or you have your F value in hertz. The difference is only 2 pi. And if you now do a Fourier analysis of that signal, you will see at 440 hertz a huge value, and you will see almost nothing anywhere else. So you have now done a Fourier analysis of a time signal, and you have decomposed it into its Fourier components, which in this case is only 440 hertz. If you did the same with the middle A of the piano, which is 440 hertz, you would see a big value here, but you would see also something at 880, and you may even see something at the third harmonic, and the same is true for a piano. And it is also for a violin. If you take a violin and you ask the violinist to produce the 440, you always get a little bit more of the 880, and you get some of 3 times the fundamental. And this is something that we can demonstrate. We have here a, admittedly somewhat poor man's version of what's called a Fourier analyzer. We take in sound for about 1/5 of a second, and then we ask the computer to Fourier analyze that for us and show us the Fourier spectrum in terms of where the frequencies were. And we will see that here, for which I think we also invented a special light condition, didn't we? The scale that you see from left to right is 2 kilohertz. I'll first make you see the 440 hertz. See that huge spike? That's at 440 hertz. So the end of the scale is 2 kilohertz. .256 hertz. Lower. I hear a flute. And remember, during the lecture on musical instruments, we believed, and I demonstrated that you can really make this one resonate only in its fundamental. I will now show you with this Fourier analyzer that there's also a little bit of the second harmonic, maybe even the third harmonic. Look at it now. You see that? That was the fundamental, second and third harmonic even. Look again. Ah! So this is a beautiful way of analyzing the frequencies in sound. I will whistle for you. Amazing. Would you have guessed it? Very nicely separated. What is the frequency? It's about here. That's about 1 kilohertz, about 900 hertz. And the second harmonic. Not so obvious. My whistle. Very high frequency. It is so high that it's off scale. And I did that purposely because I know you hate the whistle, so I didn't want you to see what it really looks like. We can listen to the radio, and then we can do a Fourier analysis on what we hear.
Hi, Kenny.
Hi there.
Have you got a question for Mr. Nader?
Oh, I don't have a question for you, actually.
I think what you're doing is
That's it.
People always hear things that are said, and maybe this will give them the context to understand that. And then also at the tail.
Too complicated for me. Any one of you want to sing? Come on. Be brave. Anyone wants to sing? Yeah.
Okay.
So all the spectrum analyzers that we have on our programs are basically Fourier analyzers?
Probably, yeah. Yeah. Says you can look at the signal, you can look to see what harmonics. Okay. So again, if you look in terms of a string, right, and you were to analyze it, so if I was looking in terms of a string, so you get something like this, right? Depending on what it is. So if this was 200, you have 400, 600, 800, so on, right?
I thought it doubled up every time, so it would be like 400, 800, 1600.
Yeah. We get all harmonics, right?
Huh?
So if the fundamental is 2,
Yeah.
then we get the second, which is 4,
Yeah.
the third, which is 6.
It's not a double of the.
No.
Okay. All right.
It's
So it's
mul-
just a continual.
Right, it's the multiples of it, right?
Okay.
Now, if I did the same thing with something that only had odd harmonics, okay? So now if you think in terms of like a closed pipe, right? So if the first one is signal is at 200, what's the next signal? Fundamental is 200. We don't get the second, 600. What's the next one after that?
No.
1,000.
Everybody likes to keep doubling.
1,000.
1,000, right? Again, you get the odd harmonic. Given it, okay? So, again, do you get,
That's,
right?
that's for closed pipe?
Yeah, so everything you do to close pipe.
Open pipe has all of them,
Right.
right?
Okay? So odd harmonic for the fundamental is 200. Again, then in Beverly it's going to be 3 times that, 5 times that, 7 times that, and so on, okay? So 2, 6, 1,000, and so on, right? And then if you get all harmonics, again, it'll be fundamental is 2, then multiply that by 2, 3, 4, 5, 6, 7, and so on. And you get all the harmonics. So yeah, from that little word then, yeah, you can look at any complex signal, or as that you can analyze it in terms of sine waves to make up that signal. And then you get those programs which are called FFTs, and you can take a signal and you can find out what frequencies are present in that signal and analyze it. So that would basically is the bulk of the stuff from chapter 7. Okay? Don't worry, there won't be any of that math that he talked about on next week's test. I know you're all disappointed by that. Okay? But if I gave you an example of something like this, you got to be able to tell me in terms of, is it all harmonics, odd harmonics, that sort of thing, right? Those sorts of things you should be able to tell me based on that.
The top one's all of it, right?
Yeah, top one is all. You got 2, 4, 6, 8, so on, right? So anything in terms of a string, where you get all harmonics, okay? Bottom one would be an example, maybe, of a closed pipe. I get odd harmonics, okay? All right, like I said for today, I didn't want to give you time to get together with your groups and again, in terms of the instrument presentations, which are next week, okay? Everybody each go, we're doing a 5 to 7 minute presentation. dealing with your instrument, okay? So maybe in terms of what are some of the physics behind how it works, okay? Those fundamental principles, okay? Again, you want to talk about probably first slide or two, basically, you know, what instruments fall within your classification. So, and then, like I said, when you talk about the physics part, if you want to, you know, deal with a particular instrument or two as a representative example as to how it works, you can do that. All right.
What other instruments do odd harmonics other than closed pipes? Is there
Okay.
anything? Does
Well, you'll probably hear that in next week's talk. Right? Everybody should be able to tell that, right? Whether they have in terms of your talks, whether it has all harmonics or odd harmonics, right? Right. So the rest of the time for today is yours to get together with your group. For some of you, you actually picked up a few new group members. So you need to get together with them and get to work on this, all right?